Hello, my name is Ademola, and this is a presentation on time series forecasting using LSTM. LSTM is abbreviation for long short-term memory. It's a type of recurrent neural network, which is good for time series forecasting. So this project is based on three separate data sets, which were obtained from the edwardsaquifer.org website, which is a website that provides information on historical data on the Edwards Aquifer, as well as sand markers and Comal Springs. So having done an initial time series analysis on these data sets, I was able to just obtain some basic exploratory information, including the minimum and maximum water level of the aquifer. I was able to visualize the patterns and trends in the data by just plotting the water level elevation against the daily high dates. I performed autocorrelation tests on the data, and I was able to obtain autocorrelation information. I also interpolated missing values in the data to reduce or minimize the effect of outliers. I interpolated the time series data sets and plotted the interpolation just to see what it looks like. I performed stationarity tests on the data and was able to confirm that the data is stationary. I calculated the 10-day moving average to be able to smooth out random variation in the data set and make it easier to identify trends and patterns. And then I plotted the moving average data against the time just to see what it looks like. And then I performed seasonal decomposition to separate the trends and the season, as well as the random time series in the data sets. So having performed the analysis, I was confident that the LSTM method is a good way of doing forecasting on these data sets. And so I went ahead and just did initial preparation of the data, which include loading the data, converting the datetime format into converting the date into time format, specified a 10-year period for this forecasting, given that the data set is a 90-year data set. And so to be able to help the computation time, I reduced the data set that I'm using for this project to just a 10-year period. And so I specified the end and the start dates. And then part of preparing the data for forecasting is splitting the data into a training, validation, and test sets. I used 40% for my training data set, 30% for validation, and 30% for testing. And then, in order to reduce the impact of extreme values and make it easier to identify patterns, I normalized the data using the mean max method, which was applied to the training, the validation, as well as the tests data sets. And then next was to create the inputs and output sequence for the LSTM model. So in creating this sequence, I specified the sequence length of 30 days. And then I created that sequence and assigned, the normalized input data for the training, the validation, as well as the testing data sets. I also defined the LSTM model architecture, which includes creating a linear stack of layers. So the sequential class was used to create the model, was specified in creating the model architecture. And then I was able to, I also went ahead and specified or added the LSTM model using the dot had function for the sequential class. And so I added a 64 LSTM neurons as the input and specified the input shape of the sequence length. And then I indicated with this one that there is just one feature in the inputs, and I also activated the layer using the ReLU activation function. I specified using the dense. I was able to specify just one output neuron for the model, for the LSTM model. Next was to compile the model using the mean squared error loss function and the Adam optimizer. The mean square error loss function helps to minimize the difference between the predicted and the actual values, while the Adam optimizer helps to adjust the weights of the model during the training and to minimize the loss function. So I set up an early stopping callback, which helps to set up a training of a maximum of 100 epochs while doing the training. But the training will stop early if validation does not improve for 10 consecutive epochs. And so my patience was specified as 10, and then the early stopping function was activated, was specified. And so trained the model using the training data set and validated the model using the validation data set. I obtained, so having trained the model, the loss that was saying was 0.002, and the mean squared error of about the same value. And then I hacked the model to perform a prediction. I then did an inverse transform of the scale data to get the actual values, and to get the actual value from the scale data. Since the values were initially transformed, and then I had to check, inverse transform them at this stage. And so I asked the model to print the first value of the output as well as the first predicted value. And then I plotted the prediction against the actual test value. So having done this process, having used the LSTM, I was able to determine that some of the advantages of a gated recurrent neural network is the ability to learn and preserve long-term dependencies in sequences, and also improved memory. Some of the limitations include one of the limitations of LSTM is that it's not good for circular referencing. So, like I said, this project is on 3 separate data sets. The other 2 are the COMAL data set as well as the sound marker. So on the COMAL, I did the same process of compiling the data, preparing data, compiling data, normalizing the data, creating the sequence, defining the architecture, and then I was able to obtain a loss of 0.0043 for the COMAL data sets, showing this plot. And so for sound markers, I was able to obtain a loss of 0.00047, the mean square error of 0.00049, and a loss of about the same amounts. And then the plot also shows that the actual and the predicted value were pretty close. Thank you.